In this episode, we look at controls that protect code, repositories, and applications from common security failures before those failures become real incidents. A modern application is more than the program a user sees on a screen. It includes source code, libraries, configuration files, build pipelines, secrets, cookies, certificates, deployment scripts, and the repositories where all of that work is stored. If those pieces are not protected, attackers may not need to break through the front door of the application. They may find a leaked password in a repository, exploit weak input handling, steal a session cookie, abuse unsigned code, or take advantage of a flaw that could have been found during review. Repository, application, and code security are about reducing those risks early. The goal is to make secure behavior part of how software is written, stored, built, tested, and trusted. Before we continue, a quick note. This audio course is part of our companion study series. The first book is a detailed study guide that explains the exam and helps you prepare for it with confidence. The second is a Kindle-only ebook with 1,000 flashcards you can use on your mobile device or Kindle for quick review. You can find both at Cyber.Me in the Bare Metal Study Guide series. A repository is a storage and collaboration location for source code and related project files. Development teams use repositories to track changes, review updates, manage versions, and coordinate work. Because repositories often contain the instructions used to build and run software, they can become extremely valuable targets. A repository may contain application code, configuration files, deployment templates, documentation, dependency lists, test data, and sometimes sensitive information that should never have been stored there. If an attacker gains access to a repository, they may learn how the application works, find weaknesses, insert malicious code, steal secrets, or prepare a more targeted attack. Protecting repositories means controlling access, reviewing changes, scanning for exposed secrets, monitoring unusual activity, and making sure code changes come from trusted people and trusted processes. Repository security matters because the application's security often begins where the code is managed. Secret scanning is the process of looking through code, repositories, configuration files, and related artifacts for sensitive values that should not be exposed. A secret may be a password, application programming interface, API, key, private key, token, database connection string, certificate, or cloud access credential. These values are dangerous when they are stored in code because repositories may be copied, forked, shared, backed up, or accessed by many people and tools. A developer may accidentally commit a secret while testing a feature. A script may include a hard-coded credential because it was convenient at the time. An old configuration file may contain a token that still works. Secret scanning helps catch these mistakes before attackers find them. It can be used before code is committed, during code review, inside continuous integration and continuous delivery, CI/CD, pipelines, or across existing repositories. When a secret is found, simply deleting it from the visible file is often not enough. Repositories keep history, which means the secret may still exist in earlier versions even after the current file has been changed. If that secret was ever exposed to an untrusted place, the safer response is usually to rotate or revoke it. Rotating means replacing it with a new secret and making the old one unusable. Revoking means disabling it completely. The application should then be updated to use the new protected value through a safer method, such as a managed secret store or protected environment variable, depending on the organization's design. The big idea is that secrets should not be hard-coded into source code. They should be stored and accessed in controlled ways, with limited permissions and logging where possible. Secret scanning reduces accidental exposure, but the follow-up action is what truly lowers the risk. Input validation is one of the most important application security ideas because applications constantly receive input. Input can come from a login form, search box, uploaded file, web request, mobile app, partner system, browser cookie, header, database field, or API call. A common mistake is assuming that input is safe because it came from a normal-looking screen or expected user path. Attackers do not have to use the application the way a normal user does. They can send unexpected characters, oversized values, missing fields, altered requests, or data designed to confuse the application. Input validation checks whether incoming data matches what the application expects before it is processed. If a field should contain a date, the application should not accept a script. If a number should be within a certain range, the application should reject values outside that range. Validation helps prevent dangerous surprises from reaching sensitive logic. Good input validation usually focuses on what is allowed, not only on what is forbidden. Trying to list every possible bad input is difficult because attackers can invent new variations. An allow-based approach defines acceptable formats, lengths, types, ranges, and values, then rejects anything that does not fit. For example, a field for a postal code can have a defined length and format. A field for a quantity can accept only appropriate numbers. A file upload can allow only specific file types and sizes. Validation should also happen on the server side, because client-side checks in a browser or mobile app can often be bypassed. Client-side checks can improve the user experience, but they should not be the only protection. The server is where the application must enforce trust. Input validation does not solve every application flaw, but it reduces the chance that hostile input will be treated as safe instructions. Input validation helps defend against several common attack patterns. Structured query language, SQL, injection happens when unsafe input is treated as part of a database command. Cross-site scripting, XSS, happens when unsafe input is placed into a web page in a way that allows script code to run in a user's browser. Path traversal happens when input is used to reach files or directories the user should not access. Command injection happens when input is passed into an operating system command in an unsafe way. These examples sound technical, but the pattern is similar. The application receives data, trusts it too much, and uses it in a dangerous context. Validation helps, but it is often paired with other controls such as output encoding, parameterized queries, safe application frameworks, least privilege, and careful error handling. The goal is to treat input as untrusted until it proves otherwise. Secure cookies are another important application control because cookies are often used to maintain sessions and remember state between requests. When you sign in to a web application, the application may issue a session cookie that helps recognize your browser during later requests. If an attacker steals or abuses that cookie, the attacker may be able to act as the signed-in user without knowing the password. Secure cookie settings help reduce that risk. One common protection marks the cookie so it is sent only over encrypted hypertext transfer protocol secure HTTPS connections. Another setting can prevent scripts in the browser from reading the cookie, which helps reduce damage from certain XSS attacks. Another setting can limit when the browser sends the cookie in cross-site situations, which helps reduce some cross-site request forgery (CSRF) risk. Cookies may seem small, but session security depends on them. Secure cookies also need sensible expiration, scope, and handling. A cookie that lasts forever creates more risk than one that expires when it is no longer needed. A cookie that is valid across too many subdomains may be exposed to parts of the environment that do not need it. A session cookie should not contain sensitive information in readable form just because it is convenient. If information must be stored in a cookie, it should be carefully protected, limited, and validated by the server. Applications should also create new session identifiers after important authentication events so attackers cannot reuse older session values. Secure cookie handling is one part of broader session management. The application needs to know who the user is, how long the session should last, when to require reauthentication, and how to end the session safely. Weak session handling can turn one stolen cookie into full account access. Static code analysis examines source code or compiled code without running the application in a live environment. Static application security testing, SAST, tools can look for patterns that may indicate vulnerabilities, insecure functions, hard-coded secrets, weak cryptography, unsafe input handling, poor error handling, or risky dependencies. The benefit is that problems can be found earlier in the development process, before the application is deployed. Developers can receive feedback while the code is still fresh in their minds, which is often cheaper and faster than fixing a flaw after release. Static analysis is also useful because it can be repeated automatically in a pipeline. Every time code changes, the scan can check for known patterns. The limitation is that static analysis can produce false positives, meaning it flags code that is not actually vulnerable. It can also miss issues that depend on runtime behavior, configuration, or business logic. Static analysis should be treated as a helpful review tool, not as a perfect judge of security. A scan finding still needs interpretation. Some findings may be serious and require immediate correction. Some may be low risk in the actual context. Some may point to coding habits that should be improved even if there is no immediate exploit path. Static analysis is strongest when it is combined with code review, developer training, dependency scanning, dynamic testing, threat modeling, and secure design practices. It also works better when teams tune rules to match their languages, frameworks, and risk priorities. If the tool produces too much noise, people may ignore it. If it is too relaxed, important issues may pass through. The practical value comes from building a feedback loop where developers learn from findings, fix real issues, and improve future code before it reaches production. Code signing is a way to prove that software came from a trusted source and has not been altered since it was signed. The developer or organization uses a signing process to create a digital signature for the code, installer, script, driver, or update. When users, systems, or operating environments later check that signature, they can verify the publisher and detect tampering. This helps protect against situations where attackers modify software, replace an update package, or distribute a fake installer that appears legitimate. Code signing does not prove that the code is free of bugs or security flaws. It proves identity and integrity. In plain language, it helps answer two questions. Who signed this software, and has it changed since they signed it? That trust can be extremely important for software updates, device drivers, scripts, mobile apps, and enterprise deployment packages. Code signing depends heavily on protecting the signing keys. If an attacker steals a signing key, the attacker may be able to sign malicious code so it appears to come from a trusted source. That can be worse than in sign malware because people and systems may be more willing to run it. This is why organizations need strong controls around signing processes, including limited access, approval workflows, logging, secure key storage, and separation of duties. Code should be reviewed and built through trusted processes before it is signed. Signing should not be treated as a decorative stamp added to anything someone wants to release. It is a trust decision. If the signing process is weak, the signature loses meaning. For Security Plus, remember that code signing supports integrity and publisher verification, but it does not replace secure coding, testing, or vulnerability management. These controls support each other across the software lifecycle. Repository access controls limit who can change code. Secrets scanning catches exposed credentials before they become an attacker's shortcut. Input validation helps applications reject unsafe data during use. Secure cookies protect session information that keeps users authenticated. Static analysis finds code-level weaknesses before release. Code signing helps users and systems trust that software has not been altered after approval. None of these controls is enough alone. A beautifully signed application can still have poor input validation. A well-written application can still be compromised if its repository contains a live cloud key. A secure cookie setting cannot save an application that accepts dangerous input everywhere. Software security is built by combining controls at different points, from the developer's workstation to the repository, pipeline, deployment process, and running application. For Security Plus questions, match the scenario to the control's purpose. If the question describes finding passwords, tokens, private keys, or cloud credentials in source code, think secret scanning. If it describes checking whether user-supplied data is the right type, size, format, or range before processing, think input validation. If it describes protecting session identifiers in a browser, think secure cookies and session security. If it describes examining code for flaws without running the application, think static analysis or SAST. If it describes proving that software came from a trusted publisher and was not modified after signing, think code signing. If it describes protecting the place where source code is stored and reviewed, think repository security. The exam may use several application terms together, so focus on the action being performed and the risk being reduced. The larger lesson is that application security begins long before an application is attacked in production. It starts with how code is stored, who can change it, what secrets are kept out of it, how inputs are handled, how sessions are protected, how code is reviewed, and how software is trusted after release. Secrets scanning reduces accidental credential exposure. Input validation helps prevent hostile data from becoming dangerous behavior. Secure cookies protect session information that attackers would love to steal. Static analysis gives teams earlier warning about code weaknesses. Code signing helps preserve trust in software origin and integrity. These controls make development and operations safer because they reduce common mistakes at the places where those mistakes are likely to happen. When you can explain each control by the risk it addresses, the topic becomes much easier to apply in both exam scenarios and real security conversations.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.